thank you, Jose Luis, and thank you, Alejandro, for inviting me here. It's a pleasure and honor to be here. I also have a student from this university in Milan, so I hope maybe in the future you can do the same and come to Milan, or we can send some students from Milan to here for their study. So my talk today is about voltage control. I know you come from different studies, so I don't know if the level of my presentation is suitable for everybody. In any case, if you feel that the level of my talk is too high or too low, you can ask me. If you don't understand some of my sentences, you can stop me, and I will try to make them easy to understand. So please feel free to stop me at any moment if something is not clear. My talk today is about voltage control. That means it's about the requirements from the power system and from power system users about voltage, and how to deal with these constraints that are imposed by typically power quality issues. Which are the tools we can use to reach these goals. So first of all, why is there any issue about voltage quality? Because typically you have voltage drops changing during the operation of the system. Why? Because loads change, so voltage drops in the power system will change, and voltage at the buses will go up and down. Typically, if you talk about load changes, these changes are very slow. So we can study these changes by using steady-state equations, power flow equations. And typically, by standards, you can find some limits for these voltage changes. For example, plus minus 10% as RMS value. But there are other types of voltage quality issues. For example, voltage sags. Typically, you have voltage sags when you have short circuits in the system, so the voltage goes down at very low values, 0 in the ideal conditions, but very close to 0 near the fault. And typically these very deep voltage sags last for the duration of the short circuit before the elimination of the short circuit by the protection systems. So you have these phenomena which are very different from the first one, typically caused by commutations, breaker operations, and so on. Then you have the flicker. It's a different type of voltage quality issue. You can have this phenomenon typically close to steel factories or industrial factories. And this cause, the flicker is the phenomenon of the lighting going up and down. Maybe you experience sometimes, you can see it. And it's very tedious for people. So that's why you have some limits given by the international standards. So 3 completely different issues. And today I will try to deal with the first one. So how to keep the voltage at load buses very close to their rated value, let's say plus 10%, for example, by means of a set of control actions. So we have, we have very high voltage systems, for example, 400 kV. Then in Italy we have the lower value for voltages is 150, 132 kV. I don't know if it's the same here. Then we have the medium voltage typically from 10 to 20, 24 kV, and then the low voltage level. So the first goal is to save voltage profiles at 400 and sub-transmission system level. Why? Because these are the backbone of the power system. So if the voltage is in good conditions at the transmission level, then probably it will be in very good conditions also for medium and low voltage levels. If you have bad voltage profiles at 400 kV, then you typically have a big problem. In 2003, in Italy, we had a blackout, but 1 month ago, in the United States, our blackout was a different story. But in the United States, 1 month before, they had probably the largest blackout ever due to a voltage problem. So in that case, the phenomenon was what we call a voltage collapse problem. And we have to keep these voltages at suitable levels, both during normal operation and following any particular type of contingency, the so-called non-critical fault. For example, if you lose a generator, if you lose a line, the voltage should stay at reasonable levels all the same. The voltage control is completely different if you deal with radial systems or meshed systems. So if you deal with radial systems, typically distribution systems, you may have some issues and some control devices relevant to this situation. Typically in the past, can I use the blackboard or the white? Is it the same? So typically in the past, distribution systems were very easy to study. Also at university we didn't pay too much attention to distribution systems in the past. So you had the grid, then a transformer, and then many feeders supply, let's say this is the high to medium voltage level, and many feeders supplying the loads and the substations medium to low voltage levels. And the power flow was always in this direction, because typically we didn't have any generation system at the distribution level. Today, probably you are aware that the situation is completely different, and due, for example, to PV, to photovoltaic, or to small micro turbines, in many hours you have that the power flow is completely reversed. So the voltage problem is completely different today from what was 10 years ago, or even 5 years ago maybe. So in the past, typically you were able to control the voltage at this busbar, and you were more or less sure that along the feeder you had reasonable values for voltages. If at the end of this feeder, for example, so you could represent the voltage in this way, going more or less down, and if in the end the voltage constraint of minus 10% was fulfilled, then you didn't have to do anything. If that constraint was not fulfilled, so if the voltage at the end of the feeder was too low, then you could, for example, compensate reactive power here, and we will see how to do it, or if you had the possibility to change the tap of that transformer, you could try to do it in order to fulfill the voltage constraint at any point of the distribution system. Okay? Today the situation is completely different. Why? Because now you have some injections of power. So, for example, the voltage could be even like this, or like this. So the type of control of this device is completely different. And it's more difficult because we electrical engineers are not used to thinking about this way of operating the radial systems. Okay, so this is the problem for distribution systems. In meshed systems, the situation is even more difficult, and it was more difficult also in the past. Why? Because the transmission system is meshed. So we cannot study very easily how the voltage goes along one feeder. You can study this feeder and the second feeder and the third feeder as they were independent. In this case, with meshed systems, you have to change completely your mind, and you need to adopt a different strategy. Why? Because, for example, if you want to control the bus, the voltage at that load bus S, you can do it in many different ways. You can try to control that voltage moving the reactive power injected by this generator or by this generator or by both, or moving, switching a capacitor or an inductor here. So you may have many different ways. And you don't know, I mean, you have to study if there are any counter action. I mean, maybe increasing the reactive power here lowers the voltage at, maybe increases the voltage here but lowers the voltage at any other bus. So you have to put all these constraints together and trying to find the best strategy. Very simple, the first approach we can think of is to reduce to an equivalent circuit. So this is bus S here, and you can use the Thevenin equivalent system, for example, by removing all generators and substituting all generators by their reactance. Okay. So here you can see different colors for the different types of reactances when you model the transmission line. So these are inductances, more or less, so let's say RL circuits. These are more or less capacitors. I think you know these kind of models. Yes? Okay. So you see that when you compute this equivalent reactance, the feature of this impedance, sorry, the feature of this impedance is reactive to the ground. Okay, so I can say, okay, this is more or less a reactance, and in particular when we deal with transmission systems, R is very small compared to X. Okay, so this is the no load voltage of this bus, and I can obtain this equivalent circuit. You should take in mind that this is not always true for distribution systems. Why? Because distribution systems typically have a resistance higher than in transmission systems, first. And second, if you have cables, you must be aware about the capacity of cables to the ground. So it's a bit different. But if we assume the inductive characteristic for this impedance, we can obtain the, I think, well-known formula for the computation of the voltage drop. This is using absolute values. This is using per unit values. So you can see that the voltage drop in a line like this one across this impedance can be computed by R times the real power plus X times the reactive power flowing through that line. I think it's well known. I can also see the same formula in a different way. So typically we studied this, we obtained this formula how? Just to compute the voltage drop. But I can change my mind and I can say, okay, I can see this as the voltage change when the load moves from one value to a different value. So instead of reasoning of voltage drop, I can say the voltage at bus S will change due to a change in PS, so due to a delta PS or due to a delta QS or both, typically both. Okay, so it's the change consequent to a change in the load. So I can compute in this way how the voltage at bus S changes due to the change in the load at the same bus in this case. This is the simplified concept of sensitivity. The concept of sensitivities, which is very important in power system, is assuming the system as linear, how a variable changes due to a change in the parameter. So in this case, how the voltage changes due to a change in the load. Okay. So reactive compensation. Why is it important, reactive compensation? Again, I assume that you somewhere talk about reactive compensation, but I think it's very easy if we look at this example. So let's assume you have this system. Is it a good operating condition? If you look at the numbers, so you see this is a generator, this is the voltage of this generator. Here I have a load and a transmission line. So looking at the numbers, do you think this system is in good conditions or not? So what are the values we should look at to answer this question? Typically, voltages, losses, okay? These are the two main issues, okay? So let's look at losses. Here I see the real power injected here, 17.6, and this is the load. So it's 1.6 megawatt lost over 16 megawatt. It's 10%. Okay, it's a bit high, but it's a bit high. But if you look at voltages, look here, you have 60 kilovolts, and here 40 kilovolts. The voltage drop is very, very high. So this is not a good operating condition. Okay, is that clear? So what can we do to improve the operating conditions? Answer? We can move to the next slide.
You can introduce reactive power in the middle.
In the middle? This is an original answer. Why in the middle? Now, let's focus first on what is the problem. Look here. You have a load. The problem is the load, essentially. It's not the line. Also because from the practical point of view, it would be very difficult to cut a line. You think of a long high voltage line. You go in the middle. You cut the line, you do something. It's very complicated, okay? It's better to operate when you have some other devices, some equipment, here or here. But what is the problem? The problem is here. The problem is that you have so this is your line, the system. You have a load, and this load takes 16 megawatt and 16 megawatts. Okay? You cannot change these two numbers. Why? Because it's the load. Your system was created just to supply that load. So you cannot change that load. What you can do is to try to compensate what is useless for the system, what creates a damage for the system. So if we look at, for example, this current, here you have a voltage and a current, right? So you will have, if the voltage is something like this, you will have a current will be something like this, okay? With this component and this component, right? What is the useful effect for the load? The energy. You have to move something, or to burn something, or to do something here. You consume 16 megawatt to move something, right? And the real power is the useful effect, which is the power associated to this current, not to this one. This one, maybe it's necessary because of the motor you have and all the equipments you have. So this is the positive effect, so you cannot change it. But what you can do is try to remove this current, which is associated with the reactive power. And how can you do it? By installing, in this case, a capacitor here. The current of this capacitor is leading the voltage. So it's like this. And if you size in such a way that the reactive power provided is exactly 16, you will have a current which is exactly opposite to this one. Okay? So if you look at the line, without this compensation, that will be the current. With the compensation installed, that will be the current. Okay? And this current is smaller than this. And the final effect for the load is the same, 16 megawatt, which is the useful effect. Okay? What is the advantage in these conditions? Lower voltage drops and lower losses on the line. So this is the reactive compensation. Of course, if this load is a capacity load, the capacitive load, that is, the current is here, it's a very rare case, but you should compensate with the opposite device, that is not a capacitor but a reactor. But it's a very rare operating condition for the load. But in some cases, you may have to install reactive compensation with reactors. For example, when you have a part of the network which is unloaded. In that case, the network unloaded is very similar to a capacitive load, and you have to compensate it with reactors here. Okay? So, coming back to this example, we need to install here a capacitor for 16 megawatts, opposite of this characteristic, that is this one. And let's look at the results. You can see that, of course, the current on this line will be lower, so lower voltage drops. You see 40 and 45. So it's 5 kilovolts, while previously we had 20 kilovolts. So the voltage conditions are much better, and also losses are improved because I lowered the current and losses are as a function of the squared current. Okay, is that clear? Last but not least, so keep in mind that the load is the same as before. I just improved my operating conditions simply adding reactive compensation. Coming back to your answer, of course you can put a capacitor here, okay? But first you should study exactly the sizing of this capacitor. And second, if I install my capacitor here, I can see the benefits along the whole line. If I install the capacitor here, I will see the benefit only from this point back to the source. Okay, so that's why this is a good point. This is just to show that the reactive compensation, and in general reactive power and voltage issues, have a very local characteristic. So you have to, you cannot act at a very general level. For example, for frequency, it's different. If you have a deficit of load, you can compensate this deficit of load by injecting real power somewhere else. Even if it's very far, you don't care. For reactive power, it's not true. So if you have a problem here, you must compensate here. You cannot do it here because it will be useless, more or less useless. Okay? Now I have the example. So I will switch to my PC. Okay. So it's a very nice program. It's nice just for teaching because you can see in this example, it's more or less the same situation as before. You can see the load and the real power and the reactive power. And here I can go to 0 for the compensation. Okay, so here I have 0 compensation, and the green arrow is the real power, and the blue arrow is the reactive power. And you can see this is the voltage drop. Here you can see what is the characteristic of this line. It's a particular line. Look at the real power injected here and injected here and withdrawn here. It's the same value. So it's a loss. Oh, very good student. It's lossless. So I assumed here that R is 0. So we will not see any effect on losses because this is a lossless line. So I will increase reactive compensation here. And you will see that the voltage here is kept at 16, while the voltage here, so you can see, increases. So here okay. So this is more or less compensation, the full compensation of this reactive power, and you can see that the voltage drop is very small. Okay. You can imagine what happens if I overcompensate the reactive power. What do you think will happen? If I overcompensate, the voltage will be higher. So you can see now that a large part of this reactive power goes into the load, but the difference goes on the line, and the direction is opposite to the real power. So this is possible. And you can see that the voltage at the end of the line is higher than the voltage at the beginning of the line. This is the so-called Ferranti effect, because it was discovered by an Italian engineer working in London. London has had a very large networking cable, so with a capacitive characteristic, and he discovered that in some operating conditions the voltage at the end of the line was higher than at the beginning, so it was really strange. And this is the reason, an overcompensation of reactive power, which is usually not acceptable. Why? Because distributors, they want to control the load over the feeder. They want to have all the power of controlling the voltage on the feeder. So in Italy at least, but I think everywhere, if you do something like this, you can receive a fine because you are overcompensating your load. Okay. Any question? Another issue, coming back to, let's say, more or less normal conditions, let's say this is the best situation. You can also see that the reactive power, in these conditions, the reactive power provided by the generator is low, let's say. Low because the compensation of the reactive losses, let's call them losses, or along the line are provided by, the compensation is provided partially by these devices and partially by the generator. If I come back to 0 here, you see that the reactive power provided by the generator is much higher because it's the generator that has to send a lot of reactive power on the line. And this may be a problem because this is an ideal generator, but real generators have some limits, some current limits, and they cannot provide any value of reactive power. At a certain point, they reach their limit, and they cannot increase 1 kilovar of their generation. In that situation, we say that they lose control of the voltage because they cannot do anything else for the system. And this is not a good condition. Okay? Any question on this example? Okay, so I will come back. Here. I don't know why it's not full screen. Thank you. Okay, thank you. Okay, advantages. We saw advantages on line losses. Line losses, it's not only a technical issues. Line losses is money because they are kilowatt hours, so you have to pay for them. But also less fuel to be burned in your power plant to provide losses, less pollution, less emissions, so a set of environmental benefits, but also lower currents. So for example, if you are the distributor, you can use smaller cross sections for your conductors if you are sure you will have reactive compensation. Or, for example, you can delay the investments if you are sure. It's a bit dangerous, but if you are sure that you will have reactive compensation, you can have a series of economic advantages. Better voltage quality. This means that your customers will be more satisfied. Better operating conditions for large generators that will have operating points far from their limits. So let's say that so far this kind of reactive compensation is the most traditional way to deal with reactive problem, especially for distribution systems. Here you can also hear about correction of the power factor, which is more or less the same. In Italy, users are, it's mandatory for users to have a power factor higher than 0.9. So you can, but it's the same issue. So it's exactly the same issue. Sometimes you have a limit on the power factor. So here you have an example, a numerical example on how to compute the requirements for the compensation system in order to satisfy this constraint. Okay, this is a picture of a capacitor installed on a distribution system. But another issue is about the influence of reactive power on voltages. Why? Because I want to move from a very simple example, this one, to a more system case where you can put all information together in order to try to coordinate all reactive resources you have in your system in order to provide a very good voltage profile. So, starting again from this simple formula and assuming the first term negligible, which is, okay, it's an assumption more or less suitable. We can also move to percentage values, and the same formula can be written in this way, where this term, do you know how we can call this term? Have you ever seen V square, V rated square divided by XS? It's what we call the short circuit capability of a bus. Never. Do you know it or not? It's not an exam, so you can answer, no, I don't know. No? Oh. Yes or no? You? Okay, so so I will try to explain in two words. So this is our system. So this is XS. This is ES and VS, okay? Let's assume you don't have this term here. I can ask you, what is the value of VS? You don't have, it's a blackboard. So in this case, let's assume I take 1 kilowatt here. What's the value of this voltage? It's equal to ES, right? This is an ideal voltage source. If I take 10 kilowatts, this value will be equal to this one. If I take 1,000 kilowatt, again, this one will be equal to this one. We refer to this situation saying that this is an infinite power source. So whatever load you withdraw from these terminals, the voltage here will not change. Okay? So I can tell that for XS equal to 0, I have an infinite power grid. Okay? If now I put an impedance here, now the situation is different. Why? Because if I increase this load, I will have a current here, the voltage drop will increase, and the voltage Vs will be lower and lower as the power increases. Okay? So I can see that I can characterize this voltage saying that it depends on this amount. This is the rated voltage, and you see that you can reverse V squared divided by XS. In the first case here, V squared divided by XS will be infinite. So it's a power in MVA, megavolt ampere. It's a power. So we say that if XS is small, the grid at these terminals will experience small, I forgot. If XS is small, that is high short circuit power, the voltage will not change as the load changes. We see that the grid is very powerful. So high short circuit power means very strong network. You can do whatever you want, the voltage will not change so much. But if XS is high, the short circuit power V squared divided by XS is not so high, will be lower, and we say that the network is weak, is not so strong. Okay? You can look at the same concept, because if you can consider this and this is the result, this is the cause. How can we control this voltage by changing the injection of reactive power? It depends on the network. So if the network is very strong, and I highlighted this ASCS, this is the short circuit capability, which is V squared divided by XS. Okay, so if this number is very high, very strong network, a change on reactive power will not affect so much the voltage. On the contrary, if the network is weak, then a change in the reactive power, a change in the load, can affect a lot the voltage. Okay? Is that clear? This is a very important concept, and very used in the practice. So can be particularly important. And this is why, for example, if you have a very disturbing load, I mean, for example, a very large factory that has a load connection and disconnection frequently, it's better to connect this very large factory to very high voltage buses, where you have the connection to the very powerful grid. The most powerful grid is the transmission grid. If you connect to those plugs a very powerful load, you will experience very deep voltage drops every time you connect this load, because excess is higher in this case. Is that clear? More or less? Okay, this is an example, numerical example. If you have a grid with where is the the short circuit power is equal to the square root of 3 times the short circuit current. This is a don't worry about that. But in this case, I computed that this is a 132 kV grid. In this case, if I want to change by 1 kilovolt the voltage of this bus, I have to inject or to change the reactive injection by 43 megavars. Okay, this is a real case. I mean, this is the real case of a sub-transmission system. If you have a higher voltage system, you will need more reactive power, because the power is more powerful. The grid is more powerful. Okay? Okay. So this was a very simple case because I had one generator and one load, one bus. Now, how can I try to control a bus, the voltage in a bus, in a 1,000 bus grid with, let's say, 200 generators and 800 loads? It's not so easy. It's not so easy because the situation is not this one. So at this point, the most important concept is the concept of sensitivities. And I will show you a practical example. These are not related to voltages, but this concept of sensitivity is very important in many fields of engineering. So here you have a very simple grid. You have this connection, and you can see that this big circle red shows you that you have an overload, because this line can carry up to, if I don't remember, well, I don't know, I can't remember exactly, but up to 100 megawatt. And the loading in these conditions is 132. So in order to make this system secure, for sure I must reduce this loading. I have many possibilities. Of course, I could shed this load, but this is not a good solution, because the goal of a power system is to supply load. So if I shed this load, my mission failed. So in this case, it's easy to understand what to do. I see that the real power is provided completely by this generator, and you have two different paths to reach this bus. And it's clear that this generator is producing 0. So if I increase this power here, and at the same time I will decrease the power provided by this generator, I will increase this power flow and decrease this one. It's easy in this case. It's less easy if you have thousands of lines and branches, but in this case it's easy. And actually, I can see that if I increase by 95 megawatt here, the situation is this one. This is a simple power flow computation. You see that 95 megawatt are going in here, and this is decreased by 30, more or less 30 megawatt. Okay. Look that also the power flow in this line, of course, changes. All these lines have the same impedance. So, and this is the slack bus. Do you know the concept of slack bus? Yes? Okay, so that's why it's easy, but you need to use your brains in any case. So this is easy to do if you try to increase this power up to this point, and okay, you say, I spent my last 10 minutes trying to solve that congestion. But you cannot do it in real time. So you need a way to compute in very quick time to compute in real time this number, 95. So I know that if this is the congestion, I can solve that congestion by increasing this power by 95 megawatt. How can you do it? You can do it using sensitivities. Because if you know the sensitivity of this power flow with respect to this injection, it's a derivative. Okay, you linearize the system. Then you know that delta P, that is 30 megawatt divided by that sensitivity, will give you 95. More or less, because it's an approximation. This system is non-linear. you are linearizing the system. So more or less, let's say. But it works. It works for currents and real power. It doesn't work for voltages and reactive power. I mean, the approximation is not so good. The reactive problem is much more non-linear than the real problem. So this is the way you can use to simplify the approach and using the fast decoupled power flow equations. Are you familiar with this? Okay. So you can try to compute these sensitivities in a very easy way, but I would like to show you how to do it in a more general way, because I can use it for also for voltages, which is the subject of this lesson. So how to compute in general analytic sensitivities? In general, the sensitivity is a number that gives you information about how state variables change with respect to some control variables. State variables typically are voltage angles, not particularly important in general, voltage magnitudes, or their combinations, currents, power flows, and so on. With respect to what? To some control variables, to some variables you can move, you can displace. For example, the injected powers. If you shed a load, if you open a breaker, you are changing the injected power. And you will have a change in angles, voltage magnitudes, currents, and so on. Okay, loads is there. If you open a breaker of a generator, again, you are changing the injected power. If you move a phase shifter, a transformer, you are changing at any bus of your system angles, voltage magnitudes, and so on. Tap changers, voltage at generators. So all these are control variables, and you can compute the linearization of voltage changes delta x. How to do it? You can use the power flow equations. So if I write power flow equations in this compact way, where x are state variables and u are control variables, I can linearize these equations, and I have, this is the power flow Jacobian. So the derivatives of these functions with respect to x times delta x plus the derivatives of the same equations with respect to u times delta u. So when you study the power flow, typically you neglect this part and you want to compute the change delta x in such a way to push to zero mismatches. Okay. Now we use the same equations in a different way. So I can write the same terms in this way, Jx. This is the normal power flow Jacobian, delta x plus Ju times delta u equal to 0, because we want an equilibrium solution. And we can obtain delta x in this way. So this matrix minus Jx to the minus 1 times Ju is the sensitivity matrix, because it's a matrix that gives you the terms inside here. For example, the term Sij gives you how the state variable I changes with respect to a change in the control variable J. Is that clear? Oh, yes.
I got lost in a point. Before you told that the linearization it works with the active power, but not very good with the active power.
In this is completely general. So here x can, in my mind, are also voltage magnitudes. Okay, U, we will see what can be U. But this is just delinearization. Then, in some cases, it works. In some other cases, you may refine your search. It depends. When you deal with, for example, current limits, and your system has no very important reactive power flows, it works very well. But if you want to compute some cross sensitivities, that is between real state variables and reactive control variables, or vice versa, in that case you must be careful, because it depends on the perturbation. If you apply a very small perturbation, a very small change on Q, for example, I can tell you can use this formula very easily because the perturbation is small, so also your error will be small. But if you say, okay, now I will change Q by 100 megavars, and then you find the results on how the voltage will change, I will tell you, okay, it depends probably on the system. You can try, but after applying the perturbation and finding the voltage change in the linear conditions, please check by carrying out a complete power flow, check that your error is not very good. So you have to try and check. I can tell you that the reactive problem is much more non-linear than the real one. So you must handle with care. Okay? But the method is this one. So you can iterate. Actually, the Newton method is an iteration of linearization, because the problem is non-linear. If you apply, if you use only the real sub-problem, for example, you can use a DC power flow, which is a linearization, actually. And it works more or less. You will never see a method similar to the DC power flow applied to the Q sub-problem, QV sub-problem, because it doesn't work. Okay?